All right. And so, yeah, so I guess this is sections 23. So, just kind of quick show of thumbs. Who's at least in section 23? If you guys all kind of touched it. Awesome. Perfect. That's what I like to hear. All right. And if you haven't, or if you haven't completely gone through it, that's all right too. But I think it makes it a little bit easier for us to go through. So let's go through. Oops. All right. So we're going to go through two parts today. So kind of crack your fingers a little bit, and I'm going to go through. When I wrote this notebook, you'll notice that I used a lot of emojis. I was having a lot of, it was just one of those days when I was writing this notebook. So those will pop up. But we're going to talk about Bayes' theorem, and basically that will lead into naive Bayes. Note that I might pause every time I say basically, because I think of Bayes every single time. But they will kind of introduce Bayes' theorem and kind of go from here. So kind of some background, because I think kind of Thomas Bayes. So Thomas Bayes was a mathematician, and like I joke is like the badass probability. This is a real shirt that I just think is hilarious. Bayes, because badass is an official last name. There is almost like a cult like kind of like following around like Thomas Bayes as a statistician probability, because the method kind of described with Bayesian statistics is like a really powerful thing. Basically the idea, well, we'll talk about what that looks like, but we'll kind of know that you might see a little bit of like Bayes out there and what people say. So why is Thomas Bayes such a badass? So what does Bayesians actually say? So I think the best explanation, which I think is beautiful, is this little article on basically why C3PO is wrong and Han Solo is a badass, and basically the Bayesian interpretation of probabilities. So I would strongly recommend going through it. I think I shared it on the cohort already, so you can kind of go through. But basically this author at this blog post basically goes like, who's kind of a quick fan of like Star Wars? I think for the most part it's like in most of people's like public consciousness, but if you haven't seen it, like just the first Star Wars, C3PO is like this robot, right? And he's basically in like, what's it like, I guess they're in space, right? So like Han Solo is like piloting around like these asteroids and stuff like this, and C3PO says this thing where he says, sir, the possibility of navigating an asteroid field is approximately 3,720 to 1. And then Han's never coming off, right? And so the idea here is like it's supposed to give enough danger, right? And what's kind of fun about this blog post, it basically says like, why was, see, they get, spoiler alert, they get through it, they don't die and crash. And so kind of like the author, I think, does a really kind of fun job of kind of framing this. Like, first of all, you know, like, why was C3PO wrong? And then he kind of goes into say, well, if also looking at like a little bit of meta, being like, well, we know it's a movie, we know they're kind of going to survive. Like, it kind of breaks the whole idea of like suspense, right? But there's enough suspense in there. And he kind of evaluates, you know, like how much suspense is realistic. But basically the idea here is that C3PO got it wrong because C3PO basically didn't have a prior. The prior is that Han Solo is a really good pilot. The idea here is that if we know Han Solo is a good pilot, we know the odds is not 3,720 to 1. Basically, it's more likely that he's actually going to pass through this versus just the average pilot, which is what C3PO probably basically comes up with. And basically this kind of goes through the idea of saying, if we don't know Han Solo as a pilot, and we just go off of essentially what we call a frequentist kind of like mentality, we basically say, oh, how many people survived going through an asteroid field versus how many people actually have tried going through, and basically said, oh, only 1 out of like 3,000 something, you know, actually survived through here. So like he kind of says like it has a record of 2 people surviving 7,440 people. But if you know Han Solo is a really great pilot, right? Then you kind of say, well, he's probably going to be better than most pilots over here that had crashed through. So the probability of him getting through the asteroid field is probably higher, which seems like a very basic idea, but it's actually really powerful. And that's what Bayes actually uses. Like, hey, if you already know a little bit about the thing you're about to do, you can actually adjust your probability or adjust essentially what we call our posterior. Basically, what we now can adjust our probability. Say, well, we know Han Solo is a good pilot, so we can actually adjust that probability over. And what's kind of fun is that he kind of adjusts it over. So you know, how good is Han Solo? And he basically calculates this out. You guys can read this through. And what's kind of fun is that he kind of runs up the chance that basically, based on the kind of the movie kind of thing, like, oh, it's a 75% chance of survival, which is like just enough for like, if it puts suspense in the movie, you know, without being like, oh, he's definitely gonna go through it. So I think it's kind of like he kind of ends up with that number. So anyway, cool read. It's not too long, but I strongly recommend checking it out.
Can you explain like that 75%? Because when I read the article, I was like, how did they go from 3,700 to 75%. That's kind of a big jump.
Yeah, and so I think it comes down to the fact that there's two parts, which we'll talk about in Bayes' theorem. There are three parts, I should say. There's the prior, which is basically how good is Han Solo of a pilot. The likelihood, which is what we started off with, was with what's it called, with C-3PO, and the posterior is our updated belief. Right? So our updated belief is 75% to like 3 and 4, right? Go through, and the prior right here is how good Han Solo is of a pilot. And basically, he comes up with this part where he says that Han Solo has a 20,001 chance of making it in a situation like this. So basically saying that Han Solo is such a badass pilot that basically like he never makes a mistake 20,000 times.
Oh, okay. That makes more sense. I read it the other way.
Mm-hmm. Oh,
Like he has worse of a chance, like this robot was wrong, and like really he has like a bigger chance. Okay, that makes sense. Thanks.
Yeah. So yeah, basically like he like definitely the author of this blog post kind of fudges the numbers a little bit to make it so it makes a good like, you know, kind of story. But I think it's also kind of like if you kind of go off as like, oh, Han Solo is such a great pilot, you know, he only makes a mistake in 1 out of 20,000. That seems like, you know, kind of like a realistic thing of a really great pilot. So that's kind of like how he ends up combining these together to get a 70% chance of surviving, which, you know, you're not 100% chance. It's enough to like give a, just enough suspense in the movie. So anyway, I thought it was a cool kind of read through.
What if it was the Millennium Falcon and not Han Solo that's actually good? Maybe he's just a crappy pilot in an awesome machine.
See the new movies, right?
No, I haven't.
Okay.
I've only seen the original Star Wars.
Oh, that purist. It's great. In the new movies, they basically imply that like the Millennium Falcon is basically doing all this stuff, which we won't go into that whole you know can of worms or whatnot. But yeah, definitely like you could updates like maybe this. The thing is that this prior has to be correct, right? If this prior is not correct, right, then all bets are off, right? If it's like, oh, it's not Han Solo, but Millennium Falcon, and instead it's like it's Han Solo piloting a different craft, right? Then this prior would change over here, and that would actually adjust kind of like the values going through. But yeah, great. Anyway, so I'm going to go back to Notebook and say, okay, cool. So what does this all mean? Basically, it's that Bayesian interpretation of probability is that we basically have an expected outcome based on some prior knowledge or belief. So you'll hear people say like your prior, or like or prior belief. And basically the idea here is like we already have some knowledge about this situation, and we're using that between the likelihood, which is basically saying, okay, well, what's the likelihood overall? And then combining that with our prior belief and making it into a new statistic. So this is actually kind of a really useful tool because we usually have a lot of ideas of what our prior is going to be, right? So kind of some extreme, like some examples of this that are not Star Wars related. If I flip a coin and it lands on heads, next time I'll flip it and it'll likely land on heads again. Clearly this is not right? Like just because you flip a coin and you flip it once and you see heads doesn't likely mean that's going to stay on heads every single time, right? But if you had a coin and you flipped it like 50 times and it landed on heads every single time, like you'd be like pretty suspicious that the next time you flip the coin, you probably think it's going to be heads. And that's because you're using prior knowledge versus we'll talk about the other faction, the frequentists. You would basically say, well, you don't know until you try it enough times and actually assign a probability, the true probability of that coin, assuming that you flipped it infinite amount of times. So what's nice is that we can actually use prior knowledge. For example, if you know a coin tends to be 50-50, right? And before you flip the coin, and you flip the coin, it's heads. Well, you know, a frequentist would have to say, well, I have to flip that coin many times before I can figure out what the probability is. But since you know most coins hit 50-50, even though you get a heads the first time, you can say, well, most coins are gonna be 50-50. So it might be, there's a slight chance that maybe this is a trick coin, but it's probably just a normal coin. And you flip it again, you get tails, right? Okay, seems about to hold up. If you started flipping your coin over and over again, and you start seeing it to be heads over and over again, then you're just like, maybe my prior was incorrect. Or you would update your prior, say, well, okay, I thought the coin was going to be 50-50, but now I know it's going to be much more likely to be closer to like, you know, heads. Like I said, like Star Wars example, Han Solo is one great pilot, so he'll likely go through the asteroid field. So the idea is like we basically use our prior knowledge. Like I mentioned, the other faction, the frequentists, right? So if you have a frequentist, basically it's kind of the opposite of this Bayesian part. And the interpretation is that the limit of the frequency comes into play after many, many trials. So basically, like, you can't really know the probability, at least the frequentist would say this, is that a pure frequentist is say, you can't really know the probability without basically doing the trial over and over and over again. You can't use other information because you just don't know. And Bayesians basically say, well, you can start off with a prior and then update your belief as basically time goes on, as you try it more and more. So the way this kind of phrase that Bayesians assign a probability to a hypothesis, and okay, this is like what I think this is going to be, versus frequentists have a hypothesis and then test it with, or determine the probability by doing repeated trials. So just know that sometimes it makes sense for you to, I think, more like a frequentist, and sometimes it makes more sense to be Bayesian. Okay, that makes sense to people? Okay. A subtle difference, but I think for the most part it makes sense. And just kind of like think in the back of your mind, like when it makes sense to be a Bayesian, when it makes sense to be a frequentist. Just kind of keep that in mind a little bit as we kind of go through this part. All right, so enough about Star Wars and frequentists and like Bayesian and stuff like that. Let's talk about Bayes' theorem, because Bayes' theorem is always going to be something like I said, like it's like put in like high regard. So kind of a fun fact about Bayes' theorem, if you run through the curriculum, you've seen Bayes' theorem already, but Bayes actually never published or even wrote down the theorem. And it's really great because the story goes that he felt it was so obvious that he didn't need to write it down. And that's kind of like saying like, oh, Bayes basically is such a badass. Like he's just like, this is obvious, right? I don't need to like write this down or formalize it anyway. Like it just makes sense, which I just think is great. But it actually was his friend, Richard Price, also another mathematician, or I guess statistician, however you want to phrase that. He went through the papers after he had died. His family said like, hey, can you go through Bayes' Thomas's, papers and just see if there's anything worth publishing? And he basically found this idea and he basically formalized it. So Bayes never actually wrote Bayes' theorem down, but his concept of Bayes' theorem actually was pulled out from this. And I don't think it was Richard Price. I can't remember who actually published Bayes' theorems first, but it's got his name now, or it's got Bayes' name. So we got for anyone who wrote it first. Anyway, so kind of getting a little classic experiment, like how Bayes actually first approaches, which I think is a really cool idea. And there's a little YouTube video here that I think was a great explanation. If you guys watch like Numberphile, with Matt Parker that kind of describes this, but actually go to Thomas Bayes' house and actually does this experiment. But the idea here is you sit behind a table. So you can imagine a table's behind me and have like a ball, like, kind of like a something that's not going to bounce around too much. And I throw the ball, and the idea is that when I throw the ball, it'll randomly land somewhere on the table. So obviously this isn't 100% right, but you can imagine if I throw it randomly right into the air and it lands on the table, it'll land somewhere. And then what happens? Okay, I see where it lands, like an assistant behind me that knows where it lands. And I toss another ball up and it lands. And so there's going to be, like, if you imagine if you were the assistant, I'm going to draw really quickly on here. If I have my table like this, and I'm like sitting right here. Okay, so I throw it behind me and the ball lands like right here. Okay, and the assistant's like watching this over, right? You can imagine someone, oops. It's an eyeball-ish. Okay, so they're watching what's going on here. And so my assistant's just a creepy eyeball. But anyway, take my first ball that lands there. And then I take my next ball. So let's go and write it with like some green or something like that. I throw the next ball and land it like randomly somewhere, like right here. And the assistant says, okay, the second ball is, or I will say like, no, I'll say the second ball. The second ball is, let's say this up and left of the first ball. And then I know, it's like, okay, that means I probably landed closer to this area, right? Because there's more chances for me to land left and up, right? So I'm like, okay, it probably means after that second ball toss, it's probably somewhere in this area. And I throw the next ball, right? And I might land it like over here, right? And it's like, oh, you're above the ball, right? So maybe not left or right. So you're above the ball. Like, okay, well, that means I'm probably in the lower part right here. And you can kind of imagine as I throw more balls, like if I land right here, you say, oh, you're, which is unlikely. I'll say like, oh, like you are to the right and below it. You're like, oh, okay, like maybe it's over here then. But then as I throw more and more over here randomly, right? So randomly distributed, I get the idea that, okay, most of my balls land to the left and to the right, I'm sorry, the left and above to this ball. So that likely means I'm in this quadrant, and we can kind of hone in closer and closer. So the idea here is that as we basically try each individual part, I get a better and better idea of where my ball is. And so even if my very first toss started off like, let's say my very first, wrote a lot. Come on, here we go. Okay, if my first toss was like right over here, I might have originally thought like, oh, it's because it's going to be up and above. I might have thought that the ball is like over here. But as I toss more and more randomly, basically I'll keep updating my belief and say, oh, okay, well, my first belief probably was wrong, like, or at least wasn't, you know, was unlikely. And that's really what the idea of Bayes' theorem comes from, or the idea of Bayesian statistics. Cool. Does this make sense to people? Yeah. Any questions on this experiment? Yeah, go for it, Andrew.
So not really a question, but just one of the things that kind of stuck in my head. One of the, like, I guess the primary difference between the two theories is like Bayes is likelihood based on the accumulation of the prior knowledge, whereas Frequentist is probability based on observations.
Yeah, I think that would be good. Sorry, go ahead.
No, that's all I was going to say.
I think that's like exactly it. Basically, the idea is that Bayes starts off with some kind of accumulation of prior knowledge, and like frequentists basically have to do like the experiment kind of seeing what's going forward. So what's powerful about Bayes is that you don't have to do a huge amount of experiments just to get an idea of what's going on. You can kind of keep updating as you're going through, which is a really powerful tool. So yeah, and so we can actually use that. And so kind of going forward, like you can kind of see up a little bit of like, kind of get the concept like what Bayesian statistics is doing. We can actually formalize this in mathematics, right? So kind of quickly just showing you a little bit what the Bayes theorem is there it is in all its glory, right? Cool, right? So it's kind of like, okay, like how to read this. So hopefully you guys have seen a little bit of probability already and how to read this, but I'm just kind of going through is that this is basically saying, you know, events A and B and P representing the probability. So the probability of A given that B, or sometimes A such that B, basically saying what's the probability of A happening given that B has already happened. And that's usually what we're trying to do, for example. So in our Star Wars example, this is saying the probability of A getting to the asteroid field, assuming that Han Solo is piloting it, right? So the idea here is like, you know, how good basically is Han Solo, based on how good Han Solo is, how likely are we going to get past this asteroid field? And essentially all we have to do is this guy right here, which is, I think I wrote this backwards. No, okay. Basically, all we need is our likelihood, which is this portion, and our prior beliefs, right? So saying, okay, what's our actual belief of like the first system there? So our prior basically saying, okay, Han Solo actually passing through, like how good of a pilot is he actually? Okay. So we kind of name these different parts: prior, posterior, and likelihood. Okay. So kind of like, no, that's a little bit what's phrased through. And with those three parts, we can actually do a pretty good job of updating our posterior using our prior, and then our likelihood is basically saying what we've already seen a little bit before. All right, so kind of some scenario time and a little bit of coding. So what we're gonna do is say, okay, pretend we got tested positive for a rare disease. You're like, okay, like that's not exciting, right? That's not a great day for you. Like you went to the hospital, got a blood test, you're like, hey, guess what? You might be sick. And you're like, what? You're like, but look, we don't know for sure. We're gonna come back tomorrow because I gotta go to lunch, the doctor says, or something like that, and says, you know what, you can sweat it out for like a day and we'll test you tomorrow and see if you have disease or not. And you're like, oh man, like I don't wanna be sick, right? And you've tested positive, right? This seems pretty like bad. So you kind of look into a little bit of like, okay, like how accurate is this test? What's going on here for this rare disease? So you look it up and you basically find out some stuff. You're like, okay, first of all, disease is super rare. Only about like 0.1% of the population has it, which, you know, it's not super, you know, super common for you to have this disease. I'm like, okay, it's not likely, but the test is 99% accurate. And note that when I say 99% accurate, I'm saying it correctly identifies whether you're sick or not. So if you're sick, 99% of the time it identifies you as being sick. And if you're not sick, if you don't have the disease, 99% of the time it detects you as not being sick. So just know there's this little distinction there. So that's when you say 99% accurate. So you're like, oh man, like, so going off of this, what's kind of your feeling going from saying the sense of like, you know, disease is super rare, but the test is 99% accurate. What do you guys think? Do you think you have the disease or not? And how likely if you do have the disease or don't have the disease? Any ideas?
It's more likely that the test is wrong than you have the disease.
So you think maybe it's more likely that the test is wrong? But the test is like 99% accurate and it said you're like sick, right?
Well, that also depends on how many people have been tested, because that population is going to be much smaller than considering 0.01% of the entire population of the world. So
Okay.
you're probably only going to get tested if you potentially have the disease, which is going to limit the size of that that sample size rather quite a bit. So you have to consider, yeah, it's 99% accurate, but maybe that sample size is 100. So it's correctly predicted 99 out of 100 people. So it's only failed one time, but then that disease, 0.01% of the population, might still be thousands of people, kind of thing.
Okay. I think you were saying, I just want to make sure I kind of essentially like be devil's advocate here, is if I was the very first person to ever get this test, and I tested positive, would my probability change if I was the 1,000th person or the millionth person to ever get this test? Assuming that accuracy doesn't change after each time person gets tested.
Well, the only reason that I was bringing that up is kind of because of what Jeffrey had said, that it's more likely that the test is wrong than you having the disease. And that is correct, but only to a certain extent considering sample size. So looking at it from that perspective, based on this, I can't tell you off the top of my head what's more likely.
Yeah, it's still kind of like, I think for the most part, did anyone else have anything else to want to add in?
I don't know. I think I'd keep they're giving you 99% accuracy of the test. You start digging into the actual validity of the numbers they're giving to you. You have a different problem than whether or not you're asking a different problem than if the given accuracies are what they are.
And I would say 99% of the tests. So it's a 99% chance that you have the disease.
Okay, yeah. I mean, like, that's I'll tell you my feeling on this. It's like, I got this, like, the instinct, like, and I've had, like, someone like this, like my wife has gotten something, like, similar, but she got a test, like, oh, no, like, what's this going to mean? Like, this is a big deal, where it's super accurate. And they tell you the test is really accurate, 99% accurate. It seems like if it says you're sick and it's super accurate, it seems like you're likely we would be sick, right? Even if it's a rare disease, it seems like we have to be there. And, of course, I think I want to mention, Andrew kind of mentioned, is you probably wouldn't have gotten the test unless you already have like symptoms of like getting this disease, right? They don't just give like tests for fun, thankfully, right? But the idea here is that, like, assuming that there's kind of like, this is the first initial part, assuming like all things are equal, it doesn't look good for you. At least that's my kind of instinct going through. And now if you go into statistics, we'll kind of see why that actually turns out to be wrong. And it's actually not just like kind of wrong. It's not like I'm going to spoil it a little bit for you guys. Turns out you're not likely to have the disease, but like, how likely do you think you have this disease? Like, remember, it's still 99% accurate, right? Like, so is it like down to like 70%, 50%, 1%? Like, how likely
something
are we
like
talking?
60% or something like that.
Okay.
I'm not sure. I might not be doing the math right.
No, they're right. Like, we're just kind of ballparking here, because I think it's kind of important to kind of get a feel for like what we think these numbers are going to be before we actually try it out. Anyone else got like a random guess, essentially?
I think it'd be lower than 50, and pretty much going off of what Jeffrey and Andrew initially said, because as they were testing, they mainly looked at people who have this disease. So,
Okay,
yeah,
cool. Yeah. For that. All right, so like lower than 50, but not like significantly lower than 50, like maybe like 40-ish%. Does that seem right, Rakeem?
Depends. Yeah, and, again, it depends on the sample, like how many samples it took and out of which population.
Okay. All right. I think that's an important part, right? The population definitely matters. Like if you're taking a population of people who already seen like that disease, that'll be bigger probably, right? The chance of you having that 0.1%, right, is going to go up higher if you already have symptoms, right? That's a different kind of population. So good point. And that's the thing too, is like maybe this kind of goes with assumptions like, I don't feel any different, and you maybe, I don't know, accidentally got the test or something like that, or just like you really wanted to test this out and just see if you had it. So think of like those genetic tests where you don't really know if you like have a disease or not, but you can basically send in your sample and just like give everything out. So let's say like, your number felt any different, like a genetic disease that comes out like later in life. So we're assuming kind of like randomness or independent of any symptoms and stuff like that. So I want to ask Jeffrey a little bit, because Jeffrey did say, it's unlikely that I have disease. How unlikely is it, Jeffrey? At least kind of like ballparking. And again, I want to emphasize, you will not be graded on this point. The grade will come in later. There inside.
I don't have an educated guess. Well, I do have an educated guess, but that's because I've been involved in the healthcare system, and I see how much incompetency there is and how much human error there is. So that, I mean, the likelihood that it's not even your sample is higher than the likelihood that you actually have the disease if it's that rare. And that's my opinion.
Give me a number then. Give me a number on this case. So just no harm in this case, right? We're going to see what that number is.
I would say 10% likely that you have the disease.
Okay, cool. And I think safely saying Jeffrey's probably the most like optimistic. Like we probably don't have the disease, right? 10%, maybe we have a 10% chance of having a disease.
No, I'm pessimistic. I'm saying that everything is broken and doesn't work at all.
Right. No, I get that. And this is where we'll assume this 99% in here includes the brokenness of the system of people swap examples and stuff like that. So like this hospital is super good at like making sure things are really accurate, and like this test is like super like common to like they're really test this out like 99% accurate, so we can believe them in that case. But you're right, if there was a real test, you probably can't assume all those parts.
This is that special hospital for the 1%ers, right?
Yeah, it's the 1%er hospital.
It's the hospital on the Millennium Falcon.
There we go, tying it all together. All right, so let's check this out. Right now we kind of talk about, I think the lowest really we have is 10%. Okay, which, I think for me, if I first heard this and not knowing anything about Bayes, I'd be like, it seems like I have that disease. And I'll tell you, like, my wife had something kind of like doing a test, and she's like, oh my gosh, I think this is, like, I tested positive. Like, we'll see. And so kind of going through here. So what does this formula look like? So I'm just going to go through a little bit. Is that we start off with our formula here, and we say the probability of us being sick, given that we were tested positive, right? So the way we can do this base formula here is saying, okay, the probability of me being sick, right? So what's the probability of me being sick regardless of the testing? What's the probability times the probability of me being positive given that I'm sick? So that's the kind of key point here. And this is basically this probability of me being positive given that I am actually sick divided by the probability of positivity is our likelihood. And so this is going to incorporate this fact. And this is what the big part is going to be interesting here. I think that's what's going to be a little, I'll be quite honest, a little unintuitive of like why it's actually not likely that you have this disease. But we want to see by how much, right? Because we're numbers people. So note that we can say the probability of being positive, it's just saying, all right, you're either sick or you're not sick, right? And there's a probability of saying, okay, there's a probability of you being sick times the probability of you being positive such that you're sick, plus the probability of you not being sick, but still testing positive. And that's what this represents here. It's saying all the possibilities of you possibly being tested positive, okay? And what's kind of cool is that we actually, and we can combine this together, right? So what's really cool is that we actually know all of these probabilities based on this information in here, at least everything except for the left side. So the probability of me being sick is just simply going to be, 0.01. So we actually know the probability of me being sick, regardless of the test, regardless of any symptoms and all that stuff, right? Just the population in general. And then the probability of being positive such that I'm sick means that the test got it right. So the probability of that is what? Based on this guy?
99.
99, right? So 99%, so 0.99, okay? And then we actually have this part. We already know probability of being sick is 0.01. Probability of being positive such that you're sick, right? So we know this part right here, which is 0.99. Probability of me not being sick, just the inverse of this, 1 minus 0.01%, times the probability of being positive such that I'm not sick. So this means that the machine made a mistake, right? And we know from, this part here, so that means 1% of the time, so 0.01, okay? So we can actually put all these numbers here and actually figure out what this is. So let's go ahead and do that. So it's nice that we could go ahead and put the calculator, but since we have programming, let's do some programming. So probability of sick is this guy right here, 0.01%. Probability of not being sick, 1 minus that sickness, right? So we can see that's pretty high, like a 99.99%. And then the probability of me being sick is 0.99, probability of not being sick or positive such that I'm sick, and probability of being positive such that I'm actually sick is 1 minus 0.99. I could just put 1%, but I like writing my numbers in there, okay? And now we have all these probabilities, and now we stick it together, and we see with probability being positive, right? So cool, we got this numerator. So one step down. Then we have the last parts, which is the prior. We have the likelihood, which is going to be this portion of the equation. So we have these parts in here. And now we can actually find this little function, find posterior. So I could have just put this together, but I think it's a little more fun this way. So if I know what the prior is and I know what the likelihood is, I can combine those together to figure out what my posterior is. Okay. So, all right. So this is kind of the final part. You kind of crack our fingers and we crack our knuckles a little bit and say, all right, let's see how likely it is. And I think we said 10% seems like the most like optimistic in the sense that we don't have the disease, right? So let's see. Answer is less than 1%. And I think this is where like most people would be like, wait, what? Like I tested positive for a test that's 99% accurate. How am I only 1% likely to actually have disease, even though I tested positive? And the real reason why is because you are in fact like just unlikely to have disease to begin with. So anyone getting this test, it's likely, assuming it's random. So this changes once you start considering symptoms and who gets the test. But assuming that like just a random person gets a test, it's unlikely that you're actually going to have this disease. So a 1% chance. So I think this is kind of a little counterintuitive. At least I think it's so. And even like I think Jeffrey, who's kind of like, you know, for whatever reasons, you know, that you have already, say, oh, it seems unlikely that you have this test. 10% still like 10 times more than this guy. So you can see that's pretty unlikely. So one way you can also do this, which I haven't, so you can see like interpretation, this makes sense. And I think sometimes Bayes theorem kind of shows like, oh, it's super counterintuitive, which I think is true. But once you break it down, it's actually not that different. So I'm going to kind of break this down into a slightly different way, which I don't know if the curriculum actually, I'm trying to remember off the top of my head. I don't think they show a branching tree of something similar for Bayes theorem. I'm going to get a little, actually, I'm just going to make a new series like one. All right, I'm going to do a little drawing here. So, and I really want to hone in this in because I think this kind of helps it understand like how Bayes theorem actually works. So basically start off with the population, right? Population. And we split it up into two camps. You are either sick, sad face, or you're not sick, right? Happy face. And we'll just go off of the numbers of like, let's say 99% of the time you are not sick, right? Or sorry, 99.99% of the time you're not sick, right? And so we're gonna just multiply this by by 100. So that means the probability of you being sick times 100 is 1. So let me go ahead and just erase this guy. So only one person out of 10,000, or sorry, out of out of 10,000. So one person out of 10,000 people are actually sick. Okay, and I'm actually going to add in another 3 zeros just to make it a little bit easier for some of the math. So we're going to start off with like 10 million people, okay, which is smaller than the population in the US. So put a little commas in here. So cool. So you can see about 1,000 people out of 10 million people are actually sick. Okay. Now what the next part comes in is like, okay, now we consider you test positive for this disease. So you can either test positive or you can test negative. And same thing if you're feeling good, right? Either test positive or you're negative, right? And so note this is the wrong result, right? And this is the right result over here. And so with positive, 99% of this, right? So that means 99 out of this, 99% of 1,000 people will be correctly identified as being sick, so positive. So that would be 990, right? People would be out of 1,000 who are actually sick versus 10 people, okay? And then over here, same thing, which if someone has a calculator to do this for me real quick, 9,999,000 times 0.99 gives us
98,999,999.01.
Wait, 98 million or
Wait.
9?
Hold on.
It's
Oh, I
9
have the
million.
next one.
Yeah, 9,899,010.
In 10, good. And that means the rest of it is 90 people for that 0.1% of 99,900,000. Wait, that seems wrong.
I think it's 990.
Thank you. 990. There we go. That looks right.
You missed a 0 between your 9 and your 1 on your upper.
Which one?
Yeah, between the 9 and the 1, there should be a 0. Yeah.
There we go. This is why we program. It's easier to do this. All right, cool. No, thank you guys. All right, so I think this is right then. 90. Okay, cool. All right, so you can see here is that like, okay, this is the breakdown. So what we say is like, hey, we only care about the ones, in this case, that are tested positive, which is this guy and this guy. And if you look at these two different groups, which group are you more likely to be in? This guy over here, even though like you're unlikely to have the disease, right? You can see here, oh wait, I think I swapped these over still. Sorry,
Yeah.
this should be swapped over. So let's say this would be it right here. This number is wrong, isn't it? 90, did I do this math right?
Yeah, so you did get those two swapped. So the big number should be on the negative of that graph.
This should definitely be negative. Sorry, everyone. This should definitely be negative. This is positive. I think this number doesn't seem quite right. Let's double check that. I'll just go ahead and do this real quick on another screen. The reason I didn't want to do this because I had too many screens open, but let's see, 9900 times 0.99, right? Okay, so I messed this number up. This should be, of course I got, wait, hold on. Sorry, everyone. 4 9s and 3 zeros. Okay, this should be 9899010. Okay, and then I do a 0.01. Should be, okay, I missed a few values on here. This should be 9,000, oops.
Oh, yeah, that was my mistake. It's
okay.
99,990. I missed a whole 100,000. It's
all right. I've done that. Like clearly I messed up too. How do I, there we go. It should be 9999. So it should be 99, so 99,990. There we go. That makes more sense. And if you do this really quickly, if you do, what's 990 divided by 9990, and that gives us about, magically about 1%. So essentially what's happening here, it's like if we did the numbers right, you can see why I can mess this up a little bit, but you can see if I have this card, you're much more likely to be in this group than over in this group. Okay, makes sense. I know that kind of took a little bit while, but hopefully that kind of gives a little more kind of idea like why this was so extreme. So going back to, yeah, go ahead.
Yes, I have a question. Because I think in the first lab for this section, that was one of the problems, but the answer in the solution is listed as 0.5 or 50%.
It might be like, I don't know if it's a different, Andrew, you know?
Yeah, it's because you are calculating it for a 1% chance of having the disease instead of 0.01% like we are here.
Yeah, so
that's kind of what threw me off as well.
Hey, good looking out.
Yeah, and that's why I guessed like 0.65 was because I was remembering what we got from that lab, and I was like, I guess I went the wrong way with my math of getting a smaller chance to have the disease. It would make our final number also much smaller instead of the other way around. So, yeah.
Okay. No, good. And it's very similar to the curriculum. The biggest difference, like you guys had said, is that it's a 0.01% chance of having disease. So it's even less likely. And even with it being less likely, well, you guys saw about what that looks like. So cool. All right. So I don't know if does the curriculum then ask what happens if you test it again? Or if you take a test again and we test positive? Does the curriculum do that one? Oh, good. This is fun. All right, so we saw there's a 1%, less than 1% chance that we're sick, right? We take the test again, okay? And a test is positive, right? What's the likelihood of us having disease now? It's gotta be higher, right? It's gotta be higher than 1% if we test positive twice, right? So what are we thinking? Throw out some numbers for me.
At this point, I'm just like, this may not be a reliable test.
No, the test is that's to make it clear. The test is 99% accurate. So it is a super reliable test. It's just that 1% of the time it makes a mistake. So that's a key point to notice about this. The test has not changed based on phase. The test is still super accurate. It's just saying based on how many things you are, if you're likely to have disease or not. So I think for the most part, if you're going to say, okay, I get this, we're going to be more likely, but it's going to be something like maybe something like 40, 50%, right? If you test twice, based on like the first time is 1% chance of having a disease and then testing for a disease. Does that seem like about what people are thinking? That's what I'm thinking.
Yeah, so with this kind of test, it would be better to take a frequentist approach compared to a Bayesian?
No, I wouldn't say that. I would say because it's still coming off the, like all these probabilities are true. It's just, I think it's very counterintuitive, I think, from based on what we see, right? And that's where I think these extreme probabilities kind of make it really hard to judge like, whoa, what's going on? So I'll kind of just go right into this then. But you guys all agree it should be more likely, right?
Yes. My question is, would our prior knowledge then become the results that we got from that first set?
That's right. So it's no longer, we don't have a 0.01% chance of being sick now. We have just about a 1% chance, 0.98, right? It's what we are, 0.098 or 0.0098 right here. So we have to update our prior. So our prior now is being updated. It's like, okay, we already tested positive for this disease, about 1%. And that's why you can see the probability of you're sick came from over here, probably ever sick, and that's going to become our new prior. And then we can just do the same function to find posterior. The likelihood hasn't changed, right? So we know the likelihood hasn't changed because it's still the same test. The test has not changed. It's the same exact test going through. In reality, you probably wouldn't have the same test going through, but assuming a secondary test, which also is 99% accurate, kind of assume that's going through, we can see it's like, okay, let's see what that likelihood is. So I won't ask you guys any numbers because I think you guys are all very like, I don't know, like what's going to happen. But we run this now. It's going to be a 96% chance of being sick. And I think this is where this kind of makes a little more sense is that we didn't know any of the probabilities and said you tested twice for being positive on this disease, it's likely that you have this disease. And this is actually kind of like, I think even Jeffrey had said is, or I can't remember who said it now, but I think it was Andrew actually, who said about the populations, like if you already have symptoms for this disease, you don't have a 0.01% chance. You have a slightly higher percent chance, which is why you don't, like in general in the medical field, you don't just get a test just for the heck of it. Because even if the test is super accurate, but it's super rare, not likely to happen. And this is one of the things too, like I said, like I had someone who did this with a genetic test and basically they had something like this. I'm like, well, you know, you have to realize that even if the test is super accurate, there's still a chance for it to be wrong, which means, and because it's super rare, it's probably not the disease. And sure enough, they did not have that disease. So kind of good thing to kind of think about. Anyway, this is Bayes' theorem. I think it's kind of, I would say, quote unquote, like unintuitive, but it kind of helps you can see the power of it to be able to like use this kind of idea to help guide you through this probability. And again, I want to make sure, make it clear is that no part of this is like, oh, this was something wrong with like our Bayes theorem and stuff like that. It's like, no, all this stuff is proper. It's just that it's just hard for us to kind of combine the probabilities easily together.
Yeah, when you think about the fact that the probability that we have the disease was multiplied by nearly 100 times going into the second test, like that makes sense that it is almost 100 times more possible now that we have it.
Yeah, I think that's a good point. It's that going from 0.01 to 1% made it 100 times more. So you can see that it significantly went up. It's just that that change is not huge, absolute wise, but relative wise, it actually was a huge change going forward. And you can imagine as we get more and more tests, you would get closer and closer to being, yeah, you're sick.